Thermodynamics 1, Chapter 4, Lecture 3, Specific Heat, Enthalpy, and Internal Energy. We know from experience that it takes different amounts of energy to raise the temperature of identical masses of substances by 1 degree. For example, we need about 4.5 kilojoules of energy to raise the temperature of 1 kilogram of iron from 20 degrees to 30 degrees C, whereas it takes about 9 times that amount of energy to raise 1 kilogram of liquid water by the same amount. So that explains there's some fundamental difference that between iron and water, and so we need some way to be able to calculate that. So we define what's known as the specific heat as the energy required to raise the temperature of a unit mass of a substance by 1 degree. So every substance is going to have a very different specific heat. So in general, this energy depends on how the process is executed. For example, if we execute it at constant pressure, are we executing it at constant volume? And so there are really two types of specific heat capacities that we're going to talk about, CV and CP. CV is known as the specific heat at constant volume. This is the energy required to raise the temperature of a unit mass of the substance by 1 degree as the volume is maintained constant. Specific heat at constant pressure is given the symbol CP, C sub P. This is the energy required to raise the temperature of the unit mass by 1 degree as the pressure is maintained constant. So formal definitions of CV and CP are given as shown. It's actually a partial derivative of the internal energy with respect to temperature while you hold the volume constant for CV. And CP is defined to be the partial derivative of the enthalpy with respect to temperature as you hold the pressure constant. So how do we calculate delta U and delta H specifically? Well, there's actually 3 methods. First, we can use the tabulated values for U and H. This is the easiest and most accurate way when the tables are readily available. We could also use the values for CV and CP. These are mathematical relationships, and we can do the integration. Of course, you know, these are this is very hard to do by hand, but by computer it's relatively simple using MATLAB or your calculators to do this. The other method you can do is you can use the average specific heat values. So this is simple and very convenient when the property tables aren't available. And the results obtained are reasonably accurate if the temperature interval is not too large. So all 3 methods can be employed for calculating delta U or delta H. So this is method 1. Method 2 is using the mathematical relationships and doing the integrals. And method 3 uses the average CV values. We'll look at an example near the end of the lecture when we use all 3 methods on a problem, and we'll compare them. There's also a relationship between CP, CV, and R. R is the gas constant. CP equals CV plus R. And this is in your SI units. On a molar basis, CP equals CV plus R as well, but it's the RU value, and these are tabulated in the table. The specific ratio varies with temperature, but its variation is rather mild. So we define this as the constant K. K is equal to CP over CV. For monatomic gases like helium, argon, etc., its value is about 1.667. And for many diatomic gases like hydrogen, oxygen, air, this K value is 1.4 at room temperature. So let's look at example 4.7. Air at 300 K and 200 kilopascals is heated at constant pressure to 600 K. Determine the change in internal energy of air per unit mass. And here we're going to use all 3 methods. We're going to use the data from the air table, A17. We're going to use the functional form of the specific heat, and I'll show you how to do that. And then we're going to do the average specific heat values from table A to B. So for using table A, you can look in table A17, which I've clipped here. And so this is for air, treating air as an ideal gas. So at 300 K, you can look up the U value. It's 214.07 kilojoules per kilogram. We can do the same thing at 600 K. We can just look the value up for the internal energy, and then we can subtract the 2. Another method to use is to use the mathematical relationship in A2C. It gives you the what the function looks like, and it's a polynomial. And the A, B, C, and D are constants. So you look up for error. Here's the A value, the B value, the C value, the D value. It also gives you the temperature range over where it's most accurate. So here you can just plug this in and actually integrate, perform the integration, and plug in the values, and you get 6,447 kilojoules per kilomole. If you divide by the molar mass, you get the delta U in kilojoules per kilogram, 222.5, which is pretty close to what we found in part A, but much more difficult. I mean, given the choice, I'd rather use method A or C. So method C uses the average value of the constant volume specific heat. So this is from table A2B. So we have 300 plus 600 K. Add those up, divide by 2, you get 450. So here we look up what 450 is, the CV average value for air. So here it'd be 450. We get 0.773, the CV value. So we just multiply that CV value 0.773 by the change in temperature, get 220 kilojoules per kilogram, which again is very, very close. This is another easy method to employ. Look at another example, example 4.9. We have a piston cylinder device initially at 0.5 cubic meters. It's filled with nitrogen gas at 400 kilopascal and 27 degrees C. We have an internal electric heater within the device is turned on and allowed to pass a current of 2 amps for 5 minutes from a 120 volt source. The nitrogen expands at constant pressure, and we have a heat loss of 2800 joules. Determine the final temperature of the nitrogen. So this is a constant pressure process. So we're going to use the enthalpy value. So we have the work in minus the Q out is delta H. Delta H is M times the change in enthalpy. And here we're going to use the specific heat at constant CP value. So it's MCP times delta T. And this is very good for a gas. Remember, this is nitrogen as a gas, so we can use this specific heat values. So the mass of the nitrogen, how do we find that? Well, we use the ideal gas law to find M. We plug in what the values are. You get 2.245 kilojoules. The electrical work in is given by the voltage times the current times the change in time. You get 72 kilojoules. So now we have everything we need to plug into the first law. Work in, we know what that is. We calculated that, 72 kilojoules. Q out, we're told, 2.8 kilojoules. The mass we calculated. CP value, we know that. T1 we know. The only thing we don't know is T2, so we can plug everything in and solve. We get T2 is 56.7 degrees C. Okay, that's the end of this chapter, and get started working the homework problems.